Hello everyone, how are we doing today? So I will go ahead and explain you what need to be done for the experiment 11, okay, atomic emission. So you go to your blackboard, okay, and then on experiment 11, if you click the first document in Word, that will give you the handout for the experiment explaining everything, and also you can find the data sheet that you need to submit in that document, the first one, okay. And then the next one is the pre-lab help, and then I have posted here link for the virtual lab. You will go to that link and then you're going to follow the link to get you to the virtual lab, flame test and atomic emission spectra. And then the first video is explaining how to do the flame test. Flame test is, now we're going to be exposing a few cations, metal cations, to flame. And you know, each element has different amounts of electrons. In the presence of the heat, these electrons get excited and go to a higher excited state. And then when it relaxes down to the ground state, it emits radiation as color. And you will see some characteristic colors for different elements. And that's what you're going to be watching in the first video. It's very exciting, very interesting to see the different colors of the different metals. So you can watch that. And then the second part is explaining about the line spectra of some atoms. We're going to be first looking at the spectrum of the visible light. You know, the visible light has, how many colors visible light has? Visible light has 7 different colors. Okay, so this experiment explains how you're going to look at those colors through the spectroscope. Okay. I hope you remember that in the lecture chapter 7, so we talk about this is the line, this visible spectrum going from wavelength 400 to 750. So using a spectroscope, you will see the device in the virtual lab. When you look through that, even if you look at the sky, or maybe you look at the incandescent bulb, you will see all the colors that you find in a rainbow going from 400 nanometers to 750 nanometers is the visible range. So starting from violet to red, you will see 7 colors, and then you will also see where the color comes in terms of range. So this is the violet range, and then the indigo, blue, green, yellow, orange, red, like that. So the range is given in that virtual lab handout. Okay, and then you can see, and this, because the visible spectrum gives us all the colors because it covers the full spectrum. Okay, and then at the same time you're going to be looking at several atoms like hydrogen. You're going to be looking at hydrogen atom, how it looks like, and then we're going to be looking at mercury, deuterium, and helium, and their spectrum would not be like the visible spectrum because they have certain number of electrons. They will give us a line spectrum. If you remember in the lecture that I explained, the line spectrum of hydrogen has 1, 2, 3, 4 lines. So this is the discharge tube that we have the gases filled in hydrogen, and when it is plugged into the electric source, due to the electricity, the hydrogen atoms get excited, and then the excited electrons will emit at 3 different areas. So the 3 different areas are going to be like this, if you remember from the lecture. So this is how the hydrogen atom looks like, and the atom has different energy levels. N equals 1, 2, 3, 4, 5. And when we excite the hydrogen atom with the electricity, they goes to a high excited state. So they are at the ground state, N equals 1 level to begin with. So they can go to a higher levels like this. Okay, so this is the ground state. They can go to a higher level, that is the absorption. And but they're not going to stay there, they're going to come back down. When they come down, the excited hydrogen atoms, when it comes to n equals 1, the first energy level, that appears in the ultraviolet region. So these violet color lines represent n equals 1 level, which is the UV region. Now if it comes in the UV region, are we able to see it? No. Okay, because it's not visible. Visible is 400 to 750. If it occurs in the visible region only, we can see. But the excited hydrogen atoms, electrons emit and comes to the ground, not the ground state, n equals 2 level. So this is the n equals 1, that's the UV photon. But when it comes to n equals 2, the principal energy level n equals 2, from the higher states, we can see line spectrum because that appears in the visible region. When it comes from n equals 3 to 2, 3 to 2, 3 to 2, that appears in the red region of the electromagnetic spectrum. Okay, and then it can come from 4 to 2, that is blue, and then it can come from 5 to 2, and then also that is blue, and then you can come from 6 to 2, that is going to be again in the visible region, in the violet region. So for the hydrogen line spectrum, we would be able to see 1, 2, 3, 4 colors. Now when you look at the virtual lab, you will see these 4 colors, how it be seen through the spectroscope. Okay, but these lines represent these transitions coming from 3, 4, 5, 6 levels to n equals 2. It's an emission. We are seeing the emission spectrum, not the absorption spectrum. So for the hydrogen, this is how the emission spectrum look like. So those 4 lines that I just showed you, so the red one, when it comes from energy level 3 to 2, that appears in the red region. And then when it comes from 4 to 2, this is in this blue region. Indigo one would be 5 to 2, and then this violet one is coming from 6 to 2 transitions. So there are 1, 2, 3, 4 lines. You will see this in the virtual lab. Okay, when you see what is the diagram that you see for the hydrogen spectral lines. Okay, so after you are done listening to this one, please go ahead and watch that virtual lab. And also you will see in the same video virtual lab for the mercury. You can see 5 lines. So there is a violet, blue, green, yellow, red. Sometimes you might not see all of these, but you might be able to see some of these. And then the strontium and neon is given here. You will not see these ones, but we're going to be looking at hydrogen, deuterium, mercury, and helium. Okay, so let's go back to our virtual lab area. All right, so now the part A is the data from the flame test. So you will watch the video, and also it's written here what are the colors that we should be seeing for each different cation. And then from the unknown, we can identify what are the unknowns by looking at the color of the flame. That is also given to you. And then the continuous spectrum. Remember, the continuous spectrum is the whole visible spectrum. When you watch the virtual video, you will see that the red, orange, yellow, green, blue, violet, they come in this range. That is also given to you. And then we also have done mercury vapor spectrum. Now these spectroscope that we use in the lab, they are not calibrated. So what we do is we're gonna go ahead and calibrate the spectroscope using mercury vapor spectrum. Okay, so here you are given with actual wavelength in nanometers and measured wavelength in nanometers, and what is the intensity and what is the color representing those wavelengths. violet, blue, green, yellow. So you are supposed to draw a calibration curve using this measured wavelength and the actual wavelength of the mercury vapor spectrum. Okay, see the actual 404.7, measured 410. So you're going to be using measured wavelength versus actual wavelength from your Excel to draw a graph. And I did that one for you just to show you how it looks like. You also can draw it yourself. And this is for the mercury vapor spectrum. So this data that I'm showing you over here, this is what obtained, the measured and then the actual. For the actual wavelength, you will put that information in your x-axis, and for the measured wavelength, you're going to put that in your y-axis. And then you know how to draw the Excel graph, and then you highlight this information also given in the handout, and then you go to scatter plot, and then you draw the graph. I did it on Excel and I am showing you here. This is how the graph should look like, and also you need to have a title for the graph and you had to label the axis. Actual wavelength going to be in the x-axis in nanometers, measured wavelength going to be in the y-axis in nanometers. So actual versus measured. So the x-axis would be the actual, y-axis would be the measured wavelength. We have 4 data, and then when you connect them, you're going to get the best fit line. And then you also need this equation from the graph for you to do some of the calculations. Okay, so this should be something that you need to obtain when you draw your Excel graph. So if you have Excel and if you have the facility to do that, please go ahead and do it yourself and see if you also can reproduce the same graph. And if you don't have access to Excel and don't know, you can use this equation that I have drawn for you. Okay. And then for the next part, let's go back now. Okay, and that is the purpose of the mercury vapor spectrum, that you need to draw the calibration curve, which is going to look like that. And then you also need to go ahead and complete this table. Okay, before the lab, show sample calculations for n initial 3 in the space provided to the right. Now, okay, so this is for the hydrogen spectrum. Okay, now for the hydrogen spectrum, remember I showed you the lines coming from n equals 3 to 2 and 4 to 2, 5 to 2, 6 to 2, 7 to 2, like that. And for all of these, n final is going to be n equals 2, because we are looking at the visible spectrum of hydrogen, and you need to go ahead and complete this table. Okay. Okay, I will show you how to do the calculations for one of these, and then you can do the same thing for the others. Let's go to our PowerPoint slides. Okay, here. Now, oh, the equations didn't come along with this? No. Okay, fine. Okay. No, not this one. I'm missing some information here. Okay, right here. Okay, great. Okay, so for the hydrogen spectrum, this is what I was looking for. Sorry about that. Hydrogen spectrum, use equation 5 to calculate delta E for each n initial listed below. For the Balmer series. Balmer series is another name for the visible series. Okay. Remember I showed you earlier these lines. Now what we are going to do here, we're going to find out what is the energy associated with each transition. And all of this is emission for all of these. N final quantum number is 2. N value is 2. And then the initials are going to be 3, 4, 5, 6. For each of these transitions, you're going to find out the delta E. we're going to find out the frequency, and also we're going to find out the wavelength. Okay, that's what now we're going to do over here. In order to do that, we're going to use this equation, Rydberg equation. Delta E equals energy final minus initial equals minus RH 1 n squared final minus 1 n squared initial. Okay, so I will show you how to do the first one. And for all of these, you're going to be using n final as n equals 2. N initial going to be these values. Okay, let's do the first one. Okay, so for the delta E, this is how you calculate delta E equals negative RH. RH, Rydberg constant, is 2.18 into 10 to the negative 18 joule. Okay, and 1 over n squared, n final. N final is going to be 2 for each case. You see here, n final is 2. So 1 over 2 squared minus n initial is going to be n initial. So these are the initial values. For the first one is 3. So 3 raised to the power 2. So if you do this calculation, 1 over 4 minus 1 over 9, and then you multiply this by 2.18 into negative 18, that's going to give you something like 3.02 into 10 to the negative 19. There would be negative 3.03 into 10 to the negative 19 joule, delta E. And this is for the first one. And that number you're going to write here, negative 3.03 into 10 to the negative 19. I mean, you should be able to write it in the proper square, okay, proper place given. 10 to the negative 19, delta E. It is negative because it's an emission. In an emission, it loses energy. It's an exothermic process, so it would be negative, makes sense. Okay, and then you use this delta E value to calculate your frequency. And then when you calculate the frequency, you can use the absolute value for the delta E. So how do you calculate the frequency? We can use this equation. To calculate the frequency, you use this E equals h nu. So then the frequency is going to be E over h. Okay, E we found 3.03 into 10 to the negative 19 joules. And then h going to be your Planck constant, 6.626 into 10 to the negative 34 joule seconds. So if I take the number that I got earlier, you divide it by the Planck constant, 6.626 into negative 34. That is 4.56, 4.57. 4.57 into 10 to the 14. So you're going to write that number 4.57 into 10 to the 14 per second in this place over here. Frequency. Okay, 4.57. So mu is going to be this number. You will write it in the space that says frequency. And then you need to find out the wavelength. So to find out the wavelength, you can use this equation, lambda. So wavelength is going to be then C over nu. C is that's not nu, that's lambda. Let me go ahead and erase that. C over frequency. Okay, C over frequency. C is the speed of light, which is 3 into 10 to the power 8 over 4.57 into 10 to the 14. Okay, and then the 3 into 10 to the power 8 is meters per second. I'm going to write it over here. 3 into 10 to the power 8 meters per second, you divide it by, everything went away, but it's okay, fine, you got it. Okay, so let me rewrite it again. Your wavelength is going to be C over frequency. C is 3 into 10 to the power 8 meters per second, and then the frequency is 5.47 into 10 to the 14 per second. So per second will cancel. So that's the wavelength. But what we want is, we want the wavelength in nanometers. So we need to convert meters to nanometers. 1 meter is equal to 10 to the power 9 nanometers. Okay, and this will give you, okay, let's see, 3 to the power 8 over 4.57 into 14 times 9, 656. So the wavelength in nanometers for the first one, 656 nanometers. 656. So you're going to write it down over there. And similarly, you do for the n initial 4, 5, 6, 7. Okay. So for each and every calculation, n final going to be 2 and n initials are going to be these values. So you calculate the delta E, you calculate the frequency, and you calculate the wavelength, 656. And I will give you the second wavelength should be around 486. But you guys will do the calculations on your own, okay? So I will leave it to you. So it's a good practice, so you can do that, okay? And you have to complete that as part of your data calculations, okay? Okay, so let's see. Let's go to the, okay. So we are done with that part, and you had to do it for all 3, 4, 5, 6, 7. Delta E, frequency, and wavelength, all of that you need to do. And then it's asking, explain why the line corresponding to n initial 7 was not visible in the emission spectrum for the hydrogen. Now remember, the hydrogen emission spectrum is visible from 400 to 750 nanometers. When you do the calculations for an initial 7, you will come up with a number for the wavelength. Once you see that number, you will figure out whether it needs to be in the visible region or it needs to be in the UV region or the infrared region by looking at the wavelength. So you should be able to answer that question. Okay. And then the next part, record the color intensity and measured wavelength for all of the lines that you see. Corrected wavelength will be obtained from your calibration curve. Sketch the line spectrum in the spectrum blank below. You don't have to sketch that, that's okay. And then, okay, so now you are given these values for the measured wavelength for the hydrogen spectrum. Red 660, aqua 490, violet 440, another violet one at 410. And for those ones, what are the corrected wavelength? So how do you get this corrected wavelength? Now to do that, we need to refer to the calibration curve that we draw with the mercury vapor spectrum. Okay, so let me show you how to do that. Okay, so these are the measured wavelengths for the hydrogen spectrum. 660, 490, 440, 410. Now we need to find out the corrected wavelengths. Okay, so how do you do that? So we need our calibration curve. So our calibration curve equation is y equals 0.9816x, 12.657. What do we have in the y-axis? Y-axis is the measured wavelength. Actual wavelength is in the x-axis. Okay, so we use this data now, this calibration curve. Let's go here. Okay, I'll go ahead and write down the equation for you here from the calibration curve. Y equals 0.9816 x plus 12.657 is what we got for the calibration curve. Now what do we have in our y-axis? Y-axis is the measured wavelength. Okay, measured wavelength. And what do we have in the x-axis? That is the actual wavelength. Now using the calibration curve, we can find out the corrected wavelength or the actual wavelength for the hydrogen spectrum. Measured wavelengths are given. You see, measured wavelengths. So which axis do we put these values? Is it going to be to the y-axis or the x-axis? Measured, right? So this should go to y-axis. So you will use this measured. Okay, you use 660 for the y-axis equals 0.9816 x plus 12.657. So by using that you can solve for the x. So if you do the calculation for the x, it would come out as 659. So for the corrected wavelength, using that equation you put 659 here. Okay, and likewise if you do for the 490, put the y value as 490 and calculate for the x, it would come to be 486. And you need to check these numbers. I did these calculations, but make sure you also do the calculations and check to see if you also get these numbers or different number. If you get a different number, of course I'm wrong, so you have to watch out for that. Okay, 440, 435, the next one, and these are the corrected wavelengths, 404. So you write down that using the equation, and then you need to write down which n initial correspond to these lines in the hydrogen spectrum. Remember we talked about earlier that n equals 2 is the final, and then n equals 3, 4, 5, 6, and then they come back to the ground state or the n equals 2 state. We see these lines. Now looking at these n initial values, you need to figure out looking at these wavelengths, which one is the n initial. Okay, so let's see. Okay, so these numbers you got for the n initial 3. If the n initial is 3 and final 2, that comes somewhere around 656, meaning this is more closer to the 700 of the spectrum, right? 700, around the 700 we have read, right? So 656. So then what should be the n initial for this one? That need to be n initial, that would be 3, right? And then another one, so the other number 486. For that one, n initial is 4, 486. And here we have exact number 486, right? Corrected wavelength, that is corresponding to n initial 4. So likewise, when you calculate the other 3, you should be able to figure out what are the n initials for these ones. That's how you find these values. Okay, and that's about this this space, how to calculate the data in this section. Okay. Okay, and that's this part over here. Okay, go back. And then it says, suppose the electron in a hydrogen atom moves from n equals 2 to n equals 1. In which region of the electromagnetic spectrum would you expect the light from this emission to appear? Provide justification for your answer. Now for this one, n equals 1. N equals 1. So let's look at where an electron emits in n equals 1. Okay, n equals 1. This is the n equals 1. So which region do we have it in? That should be in the ultraviolet region. Okay, so it is in the UV region and we will not be able to see that. Okay. And to justify that, you can even do the delta E and then find out the wavelength. But it's okay, you can just say it emits in the UV region, so we will not be able to see. Okay. All right. And then the next part, deuterium spectrum. Now for the deuterium spectrum also, you can see the colors are there, red, aqua, violet, violet, and then the measured wavelengths are given. For the corrected wavelength, you can, just like I showed you how to find out the corrected wavelength using the equation from the graph, you can find out the corrected wavelength for the deuterium spectrum. Now let's look at the deuterium and hydrogen. So the top one is the hydrogen spectrum, the other one is the deuterium spectrum. So we have measured wavelength 660, red, aqua 490, violet 4, is that a mistake? 490, maybe not, okay. Violet 410, I wonder if the violet of the deuterium is supposed to be 440, but that's okay. I believe it looks like it's a mistake. Okay. Anyway, so you can do the corrected wavelength for the numbers given, and when you look at the deuterium and hydrogen, you can see that they both have about the similar measured wavelengths. If they have the same measured wavelengths, their corrected wavelengths also going to be pretty much similar, right? And then so go ahead and calculate the corrected wavelength for the deuterium, and then it's asking you to compare the corrected wavelengths from your deuterium spectrum to the corrected wavelength from your hydrogen spectrum. You should find that they are very similar. Explain why in the space below. Now, what is deuterium? Some of you may know what is deuterium, but if you are not familiar with deuterium, deuterium is an isotope of hydrogen. Okay. Now, hydrogen. This is your hydrogen. How many electrons hydrogen has? 1 electron. How many protons hydrogen has? 1 proton. So, hydrogen 1, 1. Hydrogen has protons, 1 proton, electrons 1. There are no neutrons. And then if you have a deuterium, deuterium is isotope of a hydrogen. So how many electrons deuterium have? Deuterium have 1 electron, 1 proton, and it has a 1 neutron. Okay, so it has mass number 2. Okay, so that would be mass number for the deuterium would be 2. But these spectrum lines, why do we get these spectrum lines? That is due to the excitation of the electrons. So if you look at the hydrogen and deuterium, number of electrons are the same. Okay, so if the number of electrons are the same, so then the emission spectrum should be the same. Okay, that's what you need to explain there. The spectral lines are obtained due to the emission of the electrons, due to the emission created by electrons, but the deuterium and hydrogen have the same number of electrons, so their emission spectra are the same. Okay, and then you have the helium spectrum. So for the helium spectrum also, you have the measured wavelength, and you can do the corrected wavelengths using the equation of the graph that I showed you. Okay, and then it says compare the corrected wavelengths from your helium spectrum to the corrected wavelength from your hydrogen spectrum. You should find they are somewhat different. Explain why in the space provided below. So you can see here, for the helium you have many lines, whereas for the hydrogen you have only 4 lines. So what is the difference? Why they are different? Again, helium has 2 electrons, hydrogen has 1. The spectral lines are due to the emission of the electrons, right? So because of that, you will see 2 different line spectra for the 2 different kinds of elements. So that's what you need to write. So that is what you need to do for your experiment report sheet. And then the handout for the experiment report sheet is posted on Blackboard, and when you open it you will see all this information for the experimental data. So you fill this information in the handout posted on Blackboard, and you can submit that. Those are the data that you need to submit. Okay, watch the videos, it's fun, and you'll be able to know how to look at through the spectroscopes and how to obtain the lines and all that. Okay, that is for now. Talk to you later. Bye bye.